Alright, so the goal is to be able to compute determinants efficiently, and the idea to that is, well, it comes down to this first theorem here, which is that the determinant of a triangular matrix is just the product of its diagonal entries. So it's very easy to calculate the determinants of triangular matrices. So for example, the determinant of this matrix here is just 6. And if you wanted to see that using the cofactor expansion, you could, if you were to expand across the first column, then the definition of the determinant says that would be 3 times the determinant. If you delete that, the first row and first column, then you're doing this submatrix here, and then you can still expand across that. So you're doing 3 in parentheses. The determinant of the small matrix is 2 times the determinant of this submatrix. And the determinant of a 1 by 1 matrix is just the number itself, so that's 3 times 2 times 1, which is, of course, 6. And so for any triangular matrix, that's just the idea. If you just inductively expand, then you're just going to keep extracting diagonal entries, and they're all going to be multiplied out. So it's easy to calculate the determinant of a triangular matrix. So what we can do is we can use row operations to turn any matrix into a triangular matrix. And so we want to just keep track of the effect of these row operations. So there are 3 elementary row operations, and I'm just illustrating them here. So the first elementary row operation is if you exchange 2 rows. So if you exchange 2 rows, then the determinant changes sign. Okay, so anytime you exchange 2 rows, you have to throw in a negative into the determinant. Okay, so for example, in this example here, I exchanged the first 2 rows. So I exchanged the first 2 rows, and so the determinant changes by a sign. The other type of operation you can do is you can multiply or divide a row by something here, and you can say, how does that affect the matrix? So here's an example. If you have, if I want to know what the determinant of this matrix is, what I can do is I could divide the first row by k, and I get a new matrix. The new matrix is, well, A, B, C, D, E, F, G, H, I, and that new matrix, the determinant of the new matrix would be k times the old matrix. Well, it would be 1 over k times the old matrix, which means that the old matrix is k times the new matrix. It's kind of confusing, but it's just right here. So the point is that, so here there's a k in front of all the entries in the first row, and so if you wanted to like pull out that k or whatever, you could, and it just pulls out from the determinant. So that's like the second type of row operation. If you multiply or divide a row by a constant, then the determinant scales by that same constant. The third type of elementary row operation is you can add or subtract a multiple of one row to a different row. And when you do that, this is very convenient. The determinant doesn't actually change. This is super helpful. So sometimes it's better to just always use the third operation, because then the determinant doesn't ever change. But so the idea is that we can use these elementary row operations as long as we keep track of how they alter the determinant in order to calculate the determinant of an arbitrary matrix. We can do some row operations and make it triangular. But every time we do an operation, we have to keep track of how the determinant changes. So let's consider this matrix here. 1, 5, 3, minus 6, 9, 2, 6, 1. So the goal is to turn this into a triangular matrix, and then it's easy to calculate the determinant of it. So, for example, we can pull the 3 out from that second column. So if we pull the 3 out from the second row, I misspoke, then we get 1 minus 2, 3, 2, 6, 1. So just by using the second elementary row operation, that's what we get. And now let's put that 1 in the upper left. So let's swap the top two rows together. So if we swap rows, we get a negative sign, but nothing else will change except for swapping the top two rows together. So now this is convenient because now that we have a leading 1 there, we can use it to clear out the bottom row. So now we're going to apply a third elementary row operation, and this won't change it. This doesn't actually change anything. It doesn't, so you don't have to, the determinant won't scale or change signs or anything like that, so we're leaving the first two rows alone. And we're going to do row 3, take away 2 times row 1. That gives us 2 minus 2 times 1 is 0. That gives us 6 minus 2 times minus 2. Gives us positive 10. That gives us 1 minus 2 times 3. That's negative 5. So here, let me keep track of, I won't say exactly what the operations are, I'll just say that here we did a, here is a scaling, so this is, here we did a scaling operation. Here we did a swapping, and here we did a add a multiple of 1, add a multiple of 1 to another. So that won't actually change the determinant at all. So since we scaled, that's where the 3 comes from, and then we swapped, that brought out a negative, and then we added or subtracted a multiple. Here we actually subtracted 2 times the first row from the third row, and that doesn't actually change the determinant. And it's not yet quite triangular, but we can do the same thing. Now let's subtract, let's do a third type of elementary operation. Let's subtract 10 times the second row from the third row. So 0 minus 10 times 0 is still 0, 10 minus 10 times 1 is 0, and then minus 5 minus 10 times 5, that's minus 55. Oops, I left off the determinant. Determinant, sorry, that's it's very important. There's a determinant here. Minus 3 times the determinant of this new matrix here. It's a new matrix obtained by just doing an elementary row operation. And at this point it's already a triangular matrix, so that's just going to be minus 3 times the determinant. You just multiply all the entries. That's 1 times 1 times minus 5. So that's just 3 times minus 55, which gives you a positive 165. So that's the determinant of the matrix.